All right, ladies, today we're going to look at solid and liquid pressure. All right, I'll just explain a couple YouTube videos that I sent a while back and provide a couple examples of how we can use the formula to calculate pressure in both solids and liquids. And then, we'll follow up that with some examples for you to do later on in the day. All right, so we're going to look at first the overall definition for pressure, which is the force or thrust, which is a push acting on unit area, meaning 1 meter squared. All right, and it's calculated using the formula pressure equals force divided by area. All right, so the unit of pressure is called a Pascal. So that's written as a capital P, common A, and it is equivalent to 1 Newton per square meter, or N slash M squared, or Nm minus 2, which we'll see, right? And it's quite a small pressure, right? So it gives you an example here that an apple in your hand exerts a pressure of about 1,000 pascals. Right? We also saw, or we should remember from the video about atmospheric pressure, that atmospheric pressure is about 100,000 pascals, right? So that's the pressure that's always on us as we walk around on the surface of the earth. That's about 100,000 pascals, right? So 1 pascal is quite small. It's quite a small pressure, right? So it tells us that pressure is equal to force over area. So that means that if the same force is applied over a small area, then the pressure will be greater than if the same force is applied over a larger area. So now we look at an example with a sharp knife and a dull knife. The sharp knife exerts a larger pressure on the surface because the same force F is applied over a small area of contact. So force over a smaller area gives you a larger pressure. Again, force over a smaller area, gives you a larger pressure. That's why it's so easy for a sharp object like a pin, a needle, or a syringe to pierce the skin, because it gives a larger pressure because that force is applied over a small area. So the dull knife will be harder to penetrate your skin, right, or to cause damage, because it exerts a small pressure on the surface because the large area of contact is there, right? So the same force exerted over a larger area gives you a smaller pressure, right? For example, if you were in some mud, and you don't want to sink, you would distribute your weight, which would be your force, over a larger area. So if you stood on a flat piece of board, your weight would be distributed over a larger area, so you more than likely would not sink in the mud. But if you stand on your own 2 feet, which is a smaller area than the board, then you will sink. Another example, if a female is wearing high heel shoes, with very thin heels, then her heels will be exerting much more pressure than somebody who is wearing, for example, flat shoes, because their weight is distributed over a smaller area. It causes more pressure, right? So if we move on to a couple examples here, we have two identical cuboids, right? And they have a weight of 24 newtons, right? The green part is the face that is on the surface, right? So for the first one, the face that is on the surface has an area of 6 meter squared. I hope you see that. So it has a width of 3 meters and a length or height, whatever you want to call it, of 2 meters. So it's 3 by 2. The other one, the surface that's facing down, is 3 by 4, so that's 12 meters squared. So if you look at the pressure exerted by the same object just on different faces, we'll see that in part A, the area again is 6 meters squared, because we have a 3 meter side times a 2 meter side that's facing downwards, the green side. Right, so the pressure is the 24 Newton, which is the weight of the cuboid, right, or the weight of the box, divided by the area, which is 6 meters squared. So we get 4 pascals. So that 24 divided by 6 gives us 4. On the other side, there's a larger area now on the ground, right? It's an area of 12 meters squared, because it's 3 by 4 this time, the face that's on the surface. So the pressure now is 24 Newton, the same weight, right, because it's the same box, divided by 12 meters squared. So it's 24 divided by 12, 2 pascals. So the same object can exert different pressures depending on which face is facing down. If the smaller face is facing down on the surface, then it's a greater pressure than if the larger face is facing down on the surface. All right. So if we move on to another example, this question asks us the pressure on a surface when a force of 50 newtons acts on a surface of area 2 meters squared or 100 meters squared. Right, so again, we write the formula. It's always good to write the formula first. Pressure is equal to force divided by area, F divided by A. So in part one, we have a force of 50 newtons, it says, and it acts over an area of 2 meters squared. So that's 50 divided by 2. So we get 25 newtons per meter squared, or just 25 pascals, right? If at any time you miss something, you can always pause the video or replay it to make sure that you see what's going on. For the second one, we're having the same force apply over an area of 100 meters squared this time. So it's 50 divided by 100. So the pressure is now much less. It's 0.5 newton per meter squared, or 0.5 pascals. So again, you see the same force acting over two different areas, producing two different forces. Right, so 50 newtons over a small area of 2 meters squared gives us 25 pascals. Right, 50 newtons over an area of 100 meters squared give us 0.5 pascals. Right, another example. A pressure of 10 pascals acts on an area of 3 meters squared. What is the force acting on the area? So our initial formula is pressure equals force over area, but we need force this time. The question asks us what is the force acting on the area. So if we transpose, force is equal to pressure times area, right? So force is equal to the 10 pascals that is given multiplied by 3 meters squared. So we get 30 newtons, which is the unit for force, right? If we move on now to liquid pressure, so that's it for the solid pressure question. It's just the one formula, force over area, right? Now we're going to look at liquid pressure. So liquid pressure depends on three things, and we're going to talk about it. Right, so pressure in a liquid increases with depth, because the further down you go, the greater the weight of the liquid above you. Right, so that means that the deeper you swim in, for example, if you go into a pool, right, or even in a river, the deeper you swim down, the more pressure you feel on you, because more water is above you pressing down on you. Right. So we're going to look at figure 16.2a, where water spurts out fastest and furthest from the lowest hole. It's also important to know that pressure at one depth is acting equally in all directions. Right? So let's look at those examples here. Right. Okay. So figure 16.2a, right, we see a column of water and we have three holes. The top one, right, the water is coming out the slowest, right, and is going the least distance. This middle one is going a little bit further, but the bottom one is where it's going fastest and furthest. That's because the pressure at the lowest point is greatest. The lower down you go, the greater the pressure, right? B now is an example showing you that pressure acts equally in all directions at the same level, right? Then finally, pressure depends on the density of the liquid. So the denser the liquid, the greater the pressure at any given depth. That's because the denser the liquid, the higher the weight will be, or the heavier it will be, right? So the formula we get here, pressure caused by a liquid, pressure is equal to depth of water multiplied by the density of the water, if it's water we're talking about, or we can talk about air pressure or pressure in mercury, right, times G, which is gravitational field strength, right? So again, pressure is equal to depth, so it doesn't have to be water, right? It can be any other fluid, and remember, fluid is either a gas or a liquid. So it's the depth inside the fluid times the density of the fluid multiplied by gravitational field strength, which we know is 10 newtons per kilogram. All right? So, example. What is the pressure 100 meters below the surface of seawater of density 1,150 kilograms per meter cube? So our formula that we're working with, pressure is equal to H, which is depth, multiplied by density of the water in this case, multiplied by G. So if we apply all of that, we get that pressure is equal to a depth of 100 meters times the density, which is 1150 kilogram meter per meter cube, multiplied by G, which is 10 newtons per kilogram. And multiplying all of that, we get 1,150,000 pascals, or if we remember our prefixes, 1.15 million pascals or megapascals. So that's it. Ladies, again, rewatch the videos how many times you need to, write it down if you need to write it down. Make sure that you understand the examples that are given so that you can work through the questions that will be subscribed later. All right.